In this video, we're going to study some property of logarithms and use this to learn how to simplify certain algebraic expressions that contain logarithms. We start by looking at two properties that come from the definition of the logarithm. Namely, for any base e, log base a of 1 is always going to be equal to 0. Why? Because a raised to the 0th equals to 1. And that's what the definition of the log tells me. To what number do I need to raise a in order to get 1? And that happens to be 0. Very similarly, if I have log base a of the same number a, then this is going to turn into 1. And the reason for that is because a raised to the first power equals to a. So to what number did I have to raise a to get a? That was 1, and that's the number that I record for my logarithm here. It's very important that we also recognize these properties in terms of the logarithmic notation of base e. So when we see the natural log of 1, we should simply understand that we're dealing with this particular property, namely e raised to the 0th is 1, therefore the ln of 1 equals to 0. Similarly, ln of e, because this logarithm has base e, therefore e to the first equals to e, so the answer to this question also happens to be 1. We now deduce 3 additional very useful properties that are going to be instrumental in helping us simplify some algebraic expression containing logs. First of all, we have the so-called product property. Namely, if we have a log and that has a times b, so the product of a times b as its input, then the logarithmic function is going to split this into a sum of two terms, namely log base a of a plus log base a of b. So we note that we start off with one single log that has multiplication as its input, and we create two separate logs with the operation of addition. And this product property simply comes from the fact that for the exponential function, e raised to, say, a plus b equals to e to the a multiplied with e to the b. So the logarithmic function simply reverses as the inverse function that property, so it will turn multiplication into addition. A very similar property is the so-called quotient property. And now we're talking about division, namely log base a of a over b. So before we had that the logarithm turned multiplication into addition, so now it's going to turn its opposite operation of division into its opposite operation of addition, namely subtraction. So we have log base a of a minus log base a of b. Again, it's important to note that I start off with a single log in which I plug in the fraction a over b, and I create two separate logs, a log base a of a minus a log base a of b. Finally, the last property, which is the most important property of the logarithmic function, is the so-called power property. And this property is really one of the main reasons why we really care about logs, because anytime we're in a situation when we want to separate the base from an exponent, the only thing that can help us out is the logarithmic function, namely through the following property: log base a of, say, a raised to a power of c. What we can do here is pull the power in the parentheses here in front of the log, and this equals to c multiplied with log base a of a. So in essence, if you notice, if you have this expression a raised to the power of c and you are in need of separating the two, you should apply log to that expression, and that will enable you to pull this c in front of the logarithmic expression. So now let's use these 5 properties of logs to try to simplify some algebraic expression containing logs. So let's start with a simple example. Let's say that we're looking at ln of 2 multiplied with 3. So this one is a classic application of the product property, namely I can split the multiplication into the sum of 2 terms, namely ln of 2 plus ln of 3. Similarly, if we have, say, ln of 2 divided by, say, 27, I can write this as ln of 2 minus ln of 27. We note that the 27 was in the denominator and therefore it's going to have a minus in front of it. And now if we try to simplify this further, maybe we can do something about that 27. Let's say that we get ln of 2 minus 27 can be written as 3 cubed. And now what I can do is bring that power using the product property. So bring this 3 in front of the ln. So I get 3 multiplied with ln of 3. How about log base 5 of the cubic root of 5? So in this case we're dealing with a root, and we've learned to write roots as fractional power. So this is 5 raised to the power of 1/3 because I had the cubic root. Now once I've written it in this form, I know what to do with it because I can pull this power in front of the log. So I can simplify this into 1/3 multiplied with log base 5 of 5. And finally, what is log base 5 of 5? Well, to what power do I need to raise 5 to get the input of 5? That's 1. So this is 1/3 times 1, which just equals to 1/3. Ln of e to the 6th minus ln of e squared. So in this example, we can pull these powers, both the 6 and the 2, in front of the log. So we get 6 ln of e minus 2 ln of e. And again, we can simplify the ln of e part because it equals to 1. The reason for that is this log is base e, so I have log base e of e, which is of course 1. So this leaves me with 6 times 1 minus 2 times 1, and that's 6 minus 2, or just 4. How about the example log base 4 of 5x cubed times y? So here I have multiple terms inside the parentheses. However, all I need to do here is understand that I can apply the same rule. So I just need to understand that I'm dealing with multiplication here. So I have 5 multiplied with x cubed, and that further is multiplied with y. So I can split this into 3 separate terms, all getting a log of base 4 in front of them. So I get log base 4 of the first factor 5 plus log base 4 of the second factor x cubed, and then finally plus log base 4 of the final factor y. And finally, what I can do to simplify this expression is pull the 3 in front of the log. So I get the final answer, log base 4 of 5 plus 3 log base 4 of x, and then plus log base 4 of y. Now we notice that really I basically had 2 steps in getting to the answer. First, I split up all the terms here that came from separate factors. I got a term for 5, a term for x cubed, and a term for y. And then if there were any powers to my newly formed terms, I got to pull them in front of the log. So let's do another example similar to this one, only a little bit more complicated. Let's say I have log base 2, and now I'm going to say introduce a fraction. Let's say that I have 8 x to the 4th divided by, say, y squared. So now that I have a fraction here, I can make sure that I need to make sure that I use both the rule for the product property as well as the quotient property of the log. But here's the way to think about this. Identify first what kind of factors you have. First you have the 8, which is then multiplied with x to the 4th, that's your second factor, and finally you have that y squared. Now, based on those two properties, here's what you're going to have to do. Any term, a factor that came from the numerator, is going to receive a sign of plus. So we have 8 coming from the numerator, we got a sign of plus. Then we have this x to the 4th coming from the numerator as well, so it too has a sign of plus. Anything coming from the denominator will get a sign of minus. So now I have minus log base 2 of y squared. And now I can simplify this. First, 2 raised to what power gives me 8? That happens to be 3. Plus, I can pull this 4 in front of the log, so 4 log base 2 of x, and then minus, pull the 2 in front, so I get 2 log base 2 of y. Again, the rule to use here is whatever factors came from the denominator get a minus, whatever factors came from the numerator will get a plus. So let's look at one more example. Let's say that I have log base 3 of say x to the 6th over say 27 y cubed. So again, we first split these factors into separate terms, each having a separate log in front of it. So first I get log base 3 of x to the 6th. This is from the numerator, so we get a plus. Then the terms that come from the denominator, namely the 27 and the y cubed, because they come from the denominator, they will receive a minus, namely minus log base 3 of 27, and then also minus log base 3 of y cubed. So now let's simplify this. We get to pull the 6 in front of the log, so I get 6 log base 3 of x minus 3 raised to what power is 27, this we can do in our head, is just 3, and then minus, we pull the 3 in front and have 3 log base 3 of y, and this is the most simplest form of my expression. Finally, let's have the example log of the square root of 3x minus 5 divided by 7. So the same idea applies here. We have really a numerator and a denominator, so I'm going to split this log, which incidentally happens to be base 10 if I don't write the base. So I first get log of the numerator and then minus log of the denominator, 7. Now this is not an expression I can simplify, because 10 to what power equals to 7, well, that's a very nasty irrational number, and we have a name for it, log 7, so I'm just going to leave that expression as is. But maybe I can simplify the first one, and in fact I can, because I have this root under my expression, so I can rewrite it as the power of 1/2. And now I can pull that 1/2 in front of my log and get just log of 3x minus 5, and finally minus log 7. Now the question is, can I split this particular log any further? And the answer is no. The properties that we have for splitting logs only apply to multiplication and division, not to addition and subtraction. So sums, which is what I have here, I have in fact a difference, sums cannot be further decomposed. So once you get to an expression like this, where you have 3x minus 5, or the sum of two terms under a log, there is nothing you can do to simplify that term any further. So now let's use the same property of logs, only backwards, to now practice condensing a logarithmic expression into a single log if possible. So we're going to have to follow the steps that we did in the previous exercises just backwards. So let's see. What we need to first do is pull these powers back inside my log. So I'm going to have a log of now x to the power of 1/2, and then that 3 got pulled inside, and I have log of the parentheses x plus 1 cubed. And once I have this, now I have the sum of two logs that are the same basis, and because the operation between them is addition, I get to combine them with multiplication. So I'm going to get x to the 1/2 multiplied by x plus 1 cubed. And now I have obtained a single log, and all the previous input is under that particular log. Let's look at another example. Let's say that I have 1/3 log base 2 of x plus log base 2 of x minus 1. So in this case, I can't really follow the steps that I just used above, because there is a parenthesis here that prevents me from doing that. So what I'm going to do first is follow the indication of the parenthesis and combine the logs first together. So I'll have 1/3, and now I get to combine these two expressions into one single log, and because again the operation here is addition, I get to multiply the two inputs. So I get x times x minus 1, and now at this stage I get to pull that 1/3 inside my log. So what I obtain is an x and an x minus 1 parentheses, and then everything to the power of 1/3. Or if we want to write this as a root, I'm going to have the log base 2 of the cubic root of the expression x times x minus 1. How about the example 2 multiplied with x plus 2 minus ln of x? Well, again, let's first pull the powers in. So I get the x plus 2 parentheses here squared. I pulled this 2 back inside my ln, and then since there's no power here, I just have minus ln of x. And now finally what I can do is combine these two. Now because I have an operation of minus here, the second term is going to be written in the denominator. So now I have a single log, and inside that log I will have the parentheses x plus 2 squared divided by the x. Finally, how about log base 2 of x plus log base 3 of, say, y? And I want you to notice that here you have two different logs, namely their bases are, here in the first case 2, and in the second case you have a log base 3. And because these have different bases and are property applied to logs of the same base, I want you to be careful and understand that these cannot be combined, as they have different bases. Finally, let's look at the so-called change of basis formula. This is a formula that's very useful when you have to compute logs exactly with your calculator, and it's not one of the simple logs that you can just do in your head. So the problem with using a calculator is that the calculator really only has two buttons. Alright, so our calculators only have the buttons ln of x, which is base e, and log of x, which is base 10. So we can only compute base e and base 10 logs using our calculators. And there's a reason for that, why you don't really have log base 2 of x also as a button, because you can use this change of base formula to figure out how to go from a log base, say, 2 to a log base 10 or e. So here's the formula. If you're given, say, log base 2 of x, and you want to rewrite it base, say, 10, The way you're going to change the base here, you're going to first apply your new base, namely 10, to the input x, and that's what you get in your numerator. So you have log of the new base of x, and then in the denominator you get a factor to adjust for this change, namely still log of the new base and then of the old base. So in both of these expressions, I want you to notice that both in the numerator and in the denominator you have log of your new base, but you're going to have two separate logs, namely in the numerator log of your new base of x divided by log of still the new base, and the input now becomes the old base. So the formula for the change of base formula in general, we're going to write as log base b, this is your new base of x, divided by log base b of a. And as I said, a was your old base, and b is your new base. So let's look at another example. Let's say that we want to compute log base 2 of 12 using our calculators. Now pick your base, either e or 10. Let's go for 10 in this example. So I'm going to have log of the new base, namely 10, and now the input here becomes the input in the numerator, and then I adjust it in the denominator by log of the old base, that becomes the input in the denominator. Another example, let's say I have log base 4 of 25. Let's use base e. In this case I have ln of 25 divided by ln of 4. And now you take these numbers, you can compute ln of 25 with your calculator, and ln of 4, you just divide them and you get the desired log base 4 of 25.